Have you ever stopped to really think about the incredible engineering that makes platforms like YouTube or Netflix work so seamlessly? It's honestly astonishing how they handle billions, literally billions, of videos and users, delivering content instantly, pretty much anywhere, without a hitch. What kind of magic is actually behind that?
Yeah, it definitely feels like magic sometimes, doesn't it? But it's definitely not magic. This isn't just about designing a simple player for a video file, not at all. We're talking about crafting a system that can manage just massive global reach, ensure instantaneous content delivery, and maintain constant availability. And all that while dealing with this immense, constantly growing amount of user-generated content and just staggering traffic levels. The scale is, well, it's truly mind-boggling when you dig into it.
Right. And that's exactly why we're here today. Our mission really is to pull back the curtain a bit and explore the blueprints, the architecture of such a system. We're going to try and extract the core ideas, some, frankly, surprising solutions, and the fundamental choices that make these services tick. Hopefully helping us all understand the clever engineering behind something we often just take for granted.
Absolutely. And this deep dive, it's really tailor-made for you, the curious learner who wants to understand the how behind all this digital experience. We'll decode the complexity together, and I think, yeah, you'll probably have some serious aha moments along the way.
All right, let's unpack this then, starting at the beginning. If you strip away all the bells and whistles, what's the fundamental purpose of these platforms for the user? What do they do?
At its very core, it's about enabling a few key interactions, really. Users need to be able to upload their own videos. That's key. They need to view content from others, easily share stuff they like, and of course interact through comments and things like that. We're squarely in the world of user-generated content, and that really dictates a lot of the system's design choices.
And what's fascinating, I find, is how that core purpose quickly leads to like a dual set of requirements for the engineers building these things. Could you walk us through those?
Yeah, definitely. We usually categorize them into functional and non-functional requirement. The functional ones are basically what the user directly experiences, what they do on the site. Uploading videos, viewing them, searching for specific content, keeping track of their watch history, leaving comments. These are the explicit actions the system has to perform. But then, and this is often the bigger challenge at scale, you have the non-functional requirements. These are the underlying qualities the system must possess. It has to be highly reliable, meaning video shouldn't just disappear or get corrupted, ever. It must be highly available, so accessible 24/7 without any significant downtime. That's table stakes now. And crucially, it needs to provide a real-time viewing experience, like virtually no lags, even with billions of users hammering it. That last one, that's a huge technical hurdle.
Wow. And when you start putting some numbers to this scale, the challenge really, really hits home. Our source material points to something like, what, 1.5 billion total users with about 800 million daily active users. That's staggering. But here's a detail that really shapes the system design, the upload to view ratio. It's around 1.200. So for every, say, 100 uploads happening, there are 200 views starting per second. Just try to picture that traffic flow.
It's immense. And to truly quantify the impact of that scale, you have to look at storage and bandwidth. Imagine 500 hours of video being uploaded every single minute. Once you compress it, optimize it, that translates to about 1,500 gigabytes or 1.5 terabytes of new video data flooding the system.
One and a
Everything,
half terabytes a minute. That's
yeah,
hard to even visualize.
it is. Think of it like adding the entire contents of a pretty high-end laptop's hard drive to their servers every single minute. 24/7. It's just colossal. But storage, believe it or not, is only half the battle, delivering all that content. That requires immense outgoing bandwidth. We're talking estimates around 1.1 terabytes per second, that's TB/S, of outgoing data to serve all those views.
1.1 terabytes a second.
Yeah. To give you a sense of that, it's like streaming the entire Netflix library's worth of data, probably multiple times over, in just a few seconds. So the profound question becomes, how do you even begin to design a system that can manage that kind of sustained, frankly, astronomical demand?
It really does make you wonder, how do engineers even start to tackle something like that? Where's the starting point?
Well, you start by defining the interaction points, the ways users or even other internal systems interact with it. We call these the APIs, application programming interfaces. So you need clear APIs for the fundamental actions. Things like upload video, obviously, search video to find content, and stream video to actually watch it. These APIs are like the front doors to the whole system. Once you have those interaction points defined, then you can start to sketch out the essential components of a high-level design. First off, when you upload a video, it doesn't just, instantly appear. It first goes into a processing queue. a holding area. This queue then feeds into an encoder. And this encoder is absolutely crucial. It doesn't just process the video once, it converts it into multiple formats, multiple resolutions.
Ah, right. So it plays on my phone, on my laptop, on a big TV.
It's exactly. It ensures your video can play smoothly on everything from, say, an old smartphone with a shaky connection to a massive 4K TV on a fiber line. Next, you obviously need robust video and thumbnail storage. The actual video files and all those different formats and resolutions we just talked about, they get stored in a highly resilient distributed file storage system, something like Google's own system, Colossus, or maybe Amazon S3 if you're building on AWS. Big, reliable storage. And don't forget the thumbnails. Each thumbnail file is tiny, sure, maybe less than 3 kilobytes. But there are millions, maybe billions of them, and they're absolutely critical for letting users browse and find content. And then we have two really critical databases. There's a user database and a video database. The user database holds the essential user info ID, name, email, that kind of stuff. But crucially, the video database is kept separate. This one stores all the video metadata. Metadata being like the title, description. Exactly. Title, description, any tags, the category, total views, likes, dislikes, all that information about the video, but not the video file itself.
Okay, that separation of user data and video data, that seems like a key design choice. For someone new to this, why not just, lump it all into one giant database? Seems simpler, maybe.
That's a really great question, actually, and it gets right to the heart of optimizing systems at scale. You see, these two types of data, user info and video metadata, they have very different read and write patterns, very different demands. Your user data, like your email address or name, changes relatively infrequently, right?
Yeah, hopefully not often.
Right. But video metadata, think about the view count or the number of likes on a really popular trending video. That data is constantly being updated, sometimes many, many times per second. Trying to make one single giant database handle both those very distinct patterns efficiently becomes incredibly difficult, almost impossible at this scale.
Oh, okay.
So keeping them separate allows the engineers to optimize each database specifically for its unique workload. They might use a different type of database technology for each, or different scaling strategies, different indexing, all tailored to how that specific data behaves.
Got it. So it's about optimizing for how often the data changes, essentially, rather than a one-size-fits-all approach. That makes a lot of sense. So, okay, with all this data, especially that constantly changing video metadata being read and written all the time, how do we ensure fast access? How do you prevent those databases, even if they're separate, from becoming a huge bottleneck? This sounds like a really core challenge at scale.
It absolutely is. One of the primary strategies here, especially for the metadata storage given that immense read-write traffic, is metadata sharding. Basically, instead of one gigantic database server trying to handle everything, we distribute or shard the metadata across many, many different servers. Lots of smaller databases working together. This spreads the load out and drastically improves performance and scalability.
And I'm guessing deciding how to shard, how to split that data up, isn't exactly straightforward. There must be trade-offs.
You're absolutely right. There are different ways to do it, and engineers face some interesting trade-offs. One common approach is user-based sharding. Here, all the metadata for a single user, all their uploaded videos info is stored on one specific server shard. The advantage is it makes it really easy to query for all of a specific user's videos. You just go to that one server. But the big downside is it can lead to hot spotting.
Hot spotting.
Meaning, if one user becomes incredibly popular, just think like a huge viral content creator, all the traffic for their video metadata hits that one single server. And that poor server can get completely overwhelmed, becoming a bottleneck itself. So another approach is directory-based sharding. Here, you might determine the shard based on, say, a hash of the video ID itself. So videos are distributed more randomly across the servers based on their ID, not the user who uploaded them. This gives you excellent distribution of data and load, much less risk of hotspots. But the downside now is it's harder to retrieve all the videos for one specific user because their video metadata might be scattered across many different server shards. You'd have to query multiple places.
Ah, okay. So it really shows that complex balancing act engineers have to do, weighing different access patterns, potential bottlenecks. It's like a constant puzzle.
It really is. Designing for massive scale is all about understanding and managing these kinds of trade-offs effectively.
Now, what about efficiency? We talked about storing terabytes of new video every minute. Surely there's overlap. Let's talk about video deduplication. Because, here's a surprising fact, or maybe not so surprising. Lots of users upload the exact same viral video, right? That cat video everyone's sharing. Why should the system store, hundreds of identical copies of that cat video data.
Exactly. It would be a colossal waste of storage space and also bandwidth when people watch it. It makes no sense. So deduplication techniques are used. Things like block matching or phase correlation can computationally identify identical video content, or even just identical parts of videos, even if they're uploaded by different users, maybe with slightly different file names. The system can then smartly store only one copy of the actual underlying video data blocks.
And just point all the different uploads to that one copy.
Precisely. It saves immense amounts of storage and also significantly reduces bandwidth needed for things like internal replication or even streaming later on. Imagine the savings when some major news event happens or a new meme just explodes online. Deduplication is huge for efficiency.
Okay, so we've stored everything efficiently. We've distributed our metadata cleverly. But how do we ensure that when I hit play on my device, the video starts instantly and streams smoothly, even if I'm, say, on the other side of the planet from where the video was originally uploaded? What's going on under the hood there?
Yeah, this is where load balancing becomes absolutely critical, and it's often implemented using a really neat technique called consistent hashing. This is a powerful method that efficiently maps incoming user requests like, I want to stream this video ID to specific servers in our vast distributed system. Its main job is to ensure the load, all those millions of requests per second, is distributed as evenly as possible across all the available servers. This prevents any single server or small group of servers from getting completely overloaded and slowing things down. And what's really quite ingenious about consistent hashing is how it also helps with fault tolerance. Often it uses this clever ring structure metaphor. Imagine all your servers and all possible request hashes arranged on a virtual circle. When a server goes down, or you'd add a new server, consistent hashing ensures that only a small fraction of the keys, like video IDs, need to be remapped to a different server. Usually just the ones handled by the failed server get distributed to its immediate neighbor on the ring. It minimizes the disruption in system-wide churn, which is vital for maintaining stability in such a large system.
It's a very elegant solution.
Very clever. Okay, next up, caching. This comes up all the time in system design. What exactly are we caching here, and why is it so vital for that instant playback speed?
We're primarily caching the hot data. What does that mean? It means the most popular, most frequently accessed videos and their associated metadata. Systems like Memcache or Redis, these are specialized in-memory data stores, are designed to keep this hot data in super fast RAM, much closer, computationally speaking, to the user or the application servers making the request, compared to fetching it from the main databases or storage systems.
And this is where that 80-20 rule comes in, right?
Exactly. We famously apply the 80-20 rule, or Pareto principle here. The observation is that roughly 20% of the content, the most popular stuff, generates about 80% of the traffic. This isn't just like a neat trivia fact. It's a fundamental strategic principle for caching. By focusing our most expensive, fastest caching resources, like lots of RAM and cache servers, on that crucial 20% of hot content, we get maybe 80% of the potential performance benefit, but for a fraction of the cost and effort compared to trying to cache everything. It's all about smart resource allocation.
Right, maximize the impact. Okay, so caching helps a lot, but if we connect this to the bigger picture, for truly global delivery, making sure videos play fast in London, Tokyo, and Buenos Aires, what's the ultimate solution there?
That would definitely be the Content Delivery Network, or CDN. CDNs are basically systems of geographically distributed servers. Think of them as cache servers, but spread out all over the world. They replicate content, especially those popular videos, thumbnails, maybe even static website assets, much, much closer to the end users geographically. So when you, sitting in, say, Australia, hit play on a popular video,
it's probably not coming all the way from a server in the US.
Exactly. It's highly likely that the video stream is coming from a CDN server located right there in Australia, maybe even in your city or a nearby one. This dramatically reduces latency, the time it takes for the data to travel, which means videos start faster and are less likely to buffer during playback. It also massively offloads the main central servers, freeing them up to handle uploads, processing, and serving less popular long-tail content that might not be cached everywhere. Less popular videos might not be on every CDN node, maybe just regional ones, but for trending content and the vast majority of views. A robust CDN infrastructure is absolutely essential for that smooth, global user experience.
And underpinning all of this, the load balancing, the caching, the CDNs, is this unwavering commitment to fault tolerance, right? We touched on it with consistent hashing, but it feels like it's built in everywhere.
Oh, absolutely. At every single layer, from having redundant copies of video data stored across multiple locations in the distributed file system, to running multiple instances of every microservice, often in different data centers or availability zones, These systems are meticulously engineered to absorb failures, a server crashing, a network link failing, even an entire data center going offline without any noticeable interruption to the end user. It's like having a backup for every backup and sometimes automated systems to manage the failover. That 24/7 availability we talked about earlier, it requires constant vigilance and redundancy.
Wow. So, okay, what does this all really mean for us, the viewers? We've kind of journeyed from this mind-bending scale, billions of users, terabytes per second, all the way down to the intricate dance of APIs, specialized databases, clever sharding, smart deduplication, super fast caching, and the global reach of CDNs. It really is a testament to some incredible engineering, isn't it? All designed meticulously to make these incredibly complex interactions feel completely effortless to us.
Right. That's the key takeaway, I think. Behind every seamless streaming experience you enjoy, every video that just plays instantly, there lies this incredibly complex, carefully architected, and meticulously tuned infrastructure. And it's not just about building it once. It's a continuous process of optimizing for speed, for reliability, for cost efficiency, constantly adapting to face ever-growing demand and new technologies. It's a continuous engineering challenge, day in, day out. And frankly, it's a pretty fascinating one to study.
Definitely. So maybe here's a final provocative thought for you, the listener, to mull over. Next time you hit play on your favorite video, just take a second to consider all those hidden engineering marvels working behind the scenes. All that complexity making the content instantly available right there for you, anywhere in the world. And maybe think about this. Looking ahead, what new challenges might arise for these kinds of systems as we push towards, say, even higher resolutions like 8K or 16K, or more interactive video content, or even fully immersive virtual reality streaming experiences? The deep dive into system design, it feels like it's truly never over.